Okay, so the final talk this afternoon is from Alastair Dewhurst. And Dr. Alastair Dewhurst is a group leader of the Tier-1 group at STFC. And he's going to speak to us today about the globally distributed data management at the LHC. So Alastair, if you can share your screen and we'll go ahead. That looks great.
So can you see that and can you hear me clearly?
Yeah, both. Thanks, Alastair.
Brilliant. So thank you for the introduction, Graham. Yeah, so I'm going to be talking about well, what the Tier-1 does at RAL in its part of well, helping the LHC solve their computing data management and computing problem. So let's just start with the basics. What are we dealing here? So in order to solve the LHC's computing problem, we need a worldwide LHC computing grid. This came into, well, the original concept was, I think, in 1999, and it kind of started to actually, there was something on the ground around 2006 with data taking for the LHC starting in 2009. So what exactly happens? Well, the LHC accelerates particles to close to the speed of light, and we're getting around 40 million collisions per second during data set taking. These are recorded in a variety of experiments. The four big ones: Atlas, CMS, LHCb, and Alice. And each event is around about a few megabytes of data in size, depending on various trigger settings. And then the vast majority of that data is thrown out by hardware and online triggers to reduce the data rate to the order of a few thousand events being taken per second, and therefore a few gigabytes of data is actually being written to disk. Then this data being created at CERN, there will be a processing of that to change it into different data formats, and then this is exported around the globe. And the map that you can see on my slide, that's actually got a point where every single, yeah, all the WLCG sites are, where that may be taking data or producing, or not taking data, storing or analyzing the data, or just have some physicists there that might need access to the data. And then overall, I mean, just to give you a sense of scale, the WLCG in total, there's about 660,000 CPU cores that are analyzing the work, around 670 petabytes of online disk storage for the experiments to use in total, and just short of an exabyte of tape storage to archive all the data and other data products that aren't needed just at this moment. RAL is about, it's one of the 5 largest sites in the WLCG, and somewhere between 5 and 10% of the LHC resources it provides in total to the overall global system. Okay, so what does the future look like? Well, yeah, I mean, that was shown now as it is in 2021, but kind of what we're really looking for is for High Luminosity LHC, which is due to start in 2027. And by that point, the amount of data being taken will go up by orders of magnitude. So each experiment will be taking many exabytes of data. So there's some plots at the bottom of this slide here. So the one on the left, this is showing the disk storage. And this is just for the Atlas experiment, where they've done some predictions. And you can see that around about 2027, when High Luminosity is due to start, the amount of data being required is dramatically rising. And what's also useful is that we've been trying to work within a flat cache budget model, and if you assume that Moore's law will give you 10 to 20% capacity each year rise, then the black lines are kind of the indication of what we need to do if we just allowed technology to just advance for us, would we solve the problem? So there's an awful lot of potential for data to, we'll need a lot more data, and we need a lot of R&D to basically get the data rates down to something that's actually affordable there. And then similarly, the plot on the right shows the equivalent for tape storage there. And of course, one of the other things is not only do we have to actually store this data, but I think that the biggest challenge is we still need people, scientists still need to be able to run over all data in a timely manner. Now, when I say all data, is that, you know, the events that are captured at the LHC, you know, if the energy is the same, then it doesn't matter if it was taken in 2019 or 2030, you know, they have the same value. So there will obviously be times where, you know, data, the amount of energy in things in the LHC does change and goes up, but effectively people will want to look at, you know, every event from the start. When they do an analysis, they need to basically check that, you know, every event from the start of data to currently is actually considered for analysis, even if many are rejected because of other things. You know, you do need to process it all in order to do that. And I think the other thing that is going to be a big challenge is that we will need to adapt to a much more heterogeneous environment. And certainly, I mean, when we're looking at storage and data management here, you've got the, as well as tape and normal spinning disks, we're going to be introducing SSDs and NVMe and other types of storage are likely to be introduced as we need to find different ways of managing and analysing the data at the exabyte scale. Okay, so that was just like the introduction. So now I'm just going to talk about the RAL Tier-1, and then after I've talked about the RAL Tier-1 and kind of the hardware setup and things, I'll actually talk about more about the software and the types of things that are done for data management. Okay, so as I mentioned, what does the RAL Tier-1 do? Well, it's one of the 5 biggest sites on the grid, and then during data taking, we take about 10% of the raw data at CERN is sent to RAL to be archived on our tape service, and we've got a 100 gig dedicated link to do that. Specifically to do that. And then overall, we also have a large amount of disk and CPU, which contributes to the global pool of resources used for a range of tasks, as Monte Carlo simulation, data processing, data analysis jobs, all of those things. Because we're a tier 1, because we're one of the larger sites and more reliable sites, we do take a leading role in the more data intensive types of activities, which will be harder to run elsewhere. And also because of the size and the tape archive we've got, we're a key part in distributing the data that universities and scientists working on the LHC will need in order to do that. Okay, so I thought I'd just start right at the bottom with the network. So I mentioned the 100 gig link, but actually we've got quite large connections to, well, you know, we need to be well connected to many things. So as well as the 100 gig link to CERN, we've got multiple 100 gig links to Janet to talk to universities, and there's also a 400 gig link to the site core. And as Andy Richards mentioned earlier, we, you know, are storing, or we will be, and we are storing some data. There is an overlap between what we do for the LHC and what they do for Diamond in terms of archive. So we are sending, need to send data from them to us in order to archive it. And then we also have access to other services within scientific computing in SDFC. So that is the tape archive system, and then the cloud. So there's a large OpenStack cloud, and then other data processing things like the Jasmine HPC resource. Okay, so in terms of the services then at the tier 1, we have a large disk storage, which we give them the name of Echo. And so this is a Ceph-based storage endpoint. And it's an object store rather than a file system, and it's designed for high throughput. And when we say that, it's got about 230 storage nodes with just short of 6,000 hard drives in it. So we can get extremely high throughput because each hard disk doesn't actually need to give much throughput itself, but if they sum together, you can get, you know, truly huge rates. And we've certainly seen peaks over a terabit per second in terms of the total throughput for the cluster. In general, though, I mean, if you look at the top right, we've got a plot of the data rate. So this is literally taken sometime in the last few weeks. And regularly the reads that are being pulled out for the analysis, that's 20 to 30 gigabytes per second. And this is actually during a very quiet time because we're not taking data at the moment in order. So that's likely to go significantly higher when we actually start taking data again for the LHC. Now, Echo, we use erasure coding to ensure the data resilience, and this is 8+3, so it means that data is split into 8 chunks. So a file would come in, it would be split into 8 chunks, and then 3 parity chunks would be calculated. And then each of these 11 chunks is actually stored on a physically different machine, and therefore we can lose entire machines without it actually having, an entire machine can go out and there's no data becomes unavailable. In fact, we can lose 3 entire machines at any one time. They can be out for maintenance, or they could have just died, and we wouldn't actually lose any data during that time. So for the LHC, we have a specific or kind of more bespoke APIs or protocols. So there's Grid FTP, which some people may be familiar with the Globus protocol, but that's being phased out because by the WLCG, and we'll be replacing it with almost entirely with XRD and the WebDAV protocols as well. Having said that, one of the things that Echo does and Ceph provides is a S3 and Swift API, and this is a huge growth area because most people who are not the LHC that wish to use an object store are perfectly happy to use the industry standard they want to build on things like that. So this the S3 endpoint has been something that started to be used over the last couple of years, taking a little while to get warmed up, but effectively we now have 360 odd terabytes of data and 160 million files or objects that are stored at the S3 endpoint, and this is continuing to grow. I mean, this is like doubled in size in the last last 3 months or so, as more and more scientific communities find that actually it's really quite easy, or it's far, maybe easy is the wrong word, but if you're using industry standard protocols which are well documented and have many bits of software already built on top of them, it's an awful lot easier to use than a much more bespoke protocol that's been specifically written for high energy physics. Okay, and then just a little bit about the Echo architecture, because one of the things that we do in order to improve performance is to place caches on the worker node. So if we look in the bottom right here, there's as mentioned, there's a large Ceph cluster with the thousands of disks in, and then on each worker node we'll have jobs running, but we've also got a daemon that's running a gateway, and this is this gateway that's highlighted here. So as well as it having the plugin that actually allows it to access the storage cluster, this gateway actually has a little proxy in it as well, a proxy cache, and therefore if multiple clients are accessing the same data, they will use the cache, but what more often happens is this little cache can actually prefetch data, and that's normally what it's doing. So if a job starts requesting things, the cache will actually then just request in advance a bit more data, and then when their job or whatever gets to the next event that it's processing, that data can already be sitting on the disk or in the memory of the machine, and allow the jobs to be processed more rapidly. And then just to finish off the diagram here, over in the right, we've got the external gateway. So this is if people which support a range of protocols, and that's for transferring data to other sites. Now that has a different caching setup, because people are, if you're an external site, you normally just want to copy the whole data. So you want to, if you're doing a caching or anything like that, you do it in a different way to on a worker node where the jobs are running, where they may be requesting data for each event at a time. Okay, and then what about scaling? So, because I did mention, we're talking about ExCALIBUR. Well, actually, because Echo is a new service, entered production in 2017, and it was based on decisions made in 2015, which, in 2015, the data model, industry had grown beyond, and the likes of Amazon and Google and Microsoft having large cloud resources. They were already very well established in 2015. So it's already been designed specifically to scale, and it's following industry best practices. And I mean, while we're not quite at the scale as indicated in this XKCD cartoon, we do now basically, we try and buy things just on a rack basis. So, we don't worry about individual storage nodes, but we're just looking at, we've got effectively a formula for a rack, top of rack switch, bunch of storage nodes, few head nodes, and we just try and buy as many of them as we've got money for each year and not worry about individual servers. So, I mean, we're the second guy in this particular one. We're not quite at the scale of of allowing data centers to burn down, but we're not dealing with individual machines anymore. We're looking at larger scale, and by pushing the data across many machines, we can cope with those kind of failures. And the other thing that Ceph does is, because it spreads out the data so much, you do get very consistent performance overall, because as you request more and more transfers, they just get spread out. So it's very difficult to take down the cluster with load, because you're not going to get hotspots in the same way you would with, say, a file system, which is storing individual files on individual machines. Okay, so that was the disk system. So, I mean, the other one we're talking about data flows is the tape system. And the current system we've got is a tape system called Castor, which was designed by CERN. We've been running it since about 2006. And what we've been doing recently is we're building at the moment an evolution on that, which is called CTA. And this is really designed to cope with the data rates of the High Luminosity LHC. And it's a lot of things have been thought about in order to do that. And one of the kind of design principles when they went to build it is, well, when you've got a tape system, it's the robotics and things are extremely expensive, and it's very much designed to maximize the throughput of the tapes and the robotics, which are the expensive part of the system, in order to to cope, because that's where the bottleneck will be, if anywhere. Now, in the current system, what we have is in front of the tape drives, there's a large hard disk buffer, around 2 petabytes of storage. But the problem with this is that tapes are the ultimate in their very low latency, but actually very high throughput. And when a tape starts writing, it needs to ingest a lot of data. And so what we have is, and the plot in the middle shows this, so this is actually a write to tape at the moment. And what you can see is that there's an awful lot of lines that go down. And that's because the tape is trying to write, and even though we have memory buffers and things, that the amount of data that can be fed to the tape in order to write it at any one time doesn't keep up. And you might say, well, surely that's easy. You can just have many many disks writing to it. But we've got to remember, with the tape system, each file has to be written in series. So it's a very much a single stream thing. So it's actually surprisingly difficult to saturate a tape system when you're writing. And this is what we've been looking at and doing with CTA. It makes extensive use of SSDs and performance storage to ensure that when things are writing and recalling, that basically the tape robotics are not held up by limitations in the disk. And then just to go into a bit more detail, so yes, the whole tape system since about 2018 is being replaced. This was because Oracle stepped out of the tape market, and we had actually Oracle robots. So we replaced the Spectra, the libraries with Spectra ones, and then the whole hardware, the tape drives, the tape servers, the databases, and the disk buffer in front is all being replaced, with the intention that this will be available for the LHC towards the end of 2021, and then for Diamond and other users, they'll give us time to make all the mistakes, and then probably 6 months later they'll start migrating to it as well, and there'll be a shared system maintaining hundreds of petabytes of data for both, for basically all the RAL users. Okay, so that was me covering what's going on at the RAL site and kind of what we're doing in terms of like the underlying technology in order to scale things. So now I'm going to talk a bit more about the software that the LHC uses in order to do its data management. And notably, I'm going to be talking about Rucio and FTS. So Rucio is my next slide. What is Rucio? Well, Rucio is a piece of software which does distributed data management, and it's aimed to provide a complete and generic scientific data management service, and it's been run for over 10 years now by Atlas, and it's been picked up by a number of other communities. Now, I think the thing that Rucio is really good at is its ability to manage data in multiple locations, but that are different, heterogeneous, because there's quite a lot of products where if every service is the same, yeah, they can manage the data between them. So if they're all the same type of, if it's a, I don't know, Ceph object store or maybe a Lustre file system, yes, it knows how to talk, to interact with all of them. But where Rucio really shines is when you've just got a complete mixture and it can deal with that. And so it deals with the creation and knowing where files, where they are, transferring and deleting and then moving them around the grid. And another kind of nice thing about Rucio is the orchestration. It can do both low level and high level management policies, and this really helps users, because what you can do is with your data, you can just say something as much as, can I have 2 copies of this data? And then Rucio, you don't have to worry about where. Rucio will go and put those 2 copies of data in separate places to give you the data resilience you want, and ensure that you've got the data access you need when you need it. And you don't have to think, oh, does that site have enough quota on it or anything like that. It can manage that for you, and you can just give it rules like that, and then it has the ability to actually make a judgment and put the data there. It also provides interfaces to other systems, so workload management systems, so you can actually use this with that you can manage your data with Rucio, and then there's an interface such that other systems can talk to it in order to get their data and find out where they need to run their jobs. And it's got I think, given the amount of data that Atlas and the LHC have got and the number of years in operational experience, it's got a good set of features in order to do that. And it is kind of, in order to manage the amount of data that the LHC has got, it's just evolved to have many things. So what exactly is it actually used for? So Rucio in production, so I grabbed a plot from Atlas. So this is the sum of, going back now 5 years, total of all the pledged disks. So this is all the officially allocated disks that Atlas have to manage. And what you can see here is, if I look at the plot, that you've got the black lines here are actually the amount that politically countries and things pledged, and the red line is actually the amount that the storage endpoints were saying they've got available, summed together. And then what Rucio can do and things is that it can actually manage the data between them. So if people have created a rule that says I must have 2 copies of the data, this is known as primary, and so you can see the amount of data that is stored as primary. But then Rucio takes advantage of the fact that it doesn't want to waste space. So if somebody was to come along a bit later and say, well, actually, I only need 1 copy of that data now, it wouldn't instantly delete it. It would leave it there as a piece of secondary data, and it would be cleaned up when it was needed. So this allows Rucio as a data management, it can basically keep sites 90% full all the time with data, and it knows that it knows what it has to keep, what it can delete, but it's useful to keep around, and it can also keep additional copies of data if it's being popular with users. So if there's a particular supersymmetry sample or something that many people are analyzing, it'll keep extra copies of that, and that'll be secondary data which it can clean up when it wants. And then if for overall for Atlas, if we include the tape as well, they've got about 600 petabytes of data and about 10 billion files. CMS started to use Rucio at some point in 2020, then they migrated over, and they've got slightly smaller numbers at the moment, but kind of comparable as well. Okay, so I've been speaking about Rucio, but then the other thing I mentioned was FTS, and FTS is the file transfer service, and it's actually responsible for managing the majority of the data transfers across the WLCG. Now, you might say, well, hang on, didn't you just say Rucio was that? And the way I kind of think of it is kind of Rucio is more of the brain, in that it's thing that it does that nothing else, that's its selling point is the fact that it is intelligent enough to process rules and say with many different endpoints to figure out what the best thing to do is in order to look after your data. FTS is very much the kind of the worker drone. You give it lots of tasks such as telling it to move data from A to B, and it will do that very well. And so in 2019, which was the last year they gave statistics for it, moved 1.3 exabytes of data, which was a little over 1 billion files were moved. Now, how does FTS work then? Well, with the grid, most of the storage endpoints will support something called third-party copies, which is where a third party, e.g. the FTS or a user, can basically request transfers from site A to site B, and it will happen directly rather than proxying it through a service. So the FTS service is not siphoning, an exabyte of data through it. It manages this, and the data is being moved directly between the sites. But what FTS does do is it can then optimize it, because if you think about a site, nothing works in isolation. You're not looking at just CERN to RAL. You've got within the WLCG, you've got CERN sending the data to RAL, to France, to Germany, to the US, and therefore all of these transfers need to be managed, and they will affect each other. If there's a huge number of transfers going from CERN to the US, probably there's going to be less transfer available to go from CERN to the UK. And this is what it does. So there's a couple of plots here that I show, and basically this is, I picked a channel at random that happened to actually not be doing terribly well, and you can see that this is the success rate of the transfers, and as the success rate isn't doing very well, the FTS service decides to back down on the number of simultaneous transfers. So on this side is the percentage of transfers that are succeeding, and this side is the number that the FTS will allow along this end between these two sites at any one time. So as the failure rate is quite poor, it drops it down and just tries to manage a few at a time. And then on this side, what you can see is that it shows the kind of the throughput. So this is the EMA, which is the exponential moving average, which is the best thing to try and estimate the average transfer speed between these two sites. And then it can also look at file size as well, because traditionally, if you've got lots of small files, they will transfer slower because there's an overhead to start. So if it detects that lots of small files are being transferred, it will increase the number of simultaneous transfers between the sites to try and compensate. So this is what the FTS is basically doing behind the scenes. So a user can come along and say, can I have 2 copies of this data? Rucio will decide where that data should be, and then the FTS service actually manages the transfers between the sites, repeats them if there's failures, to do that in the most efficient way. Okay, so what about the future then and things? So one of the things that the WLCG is working on is this concept of a data lake. And I mean, I basically think of the data lake as, at the moment, the LHC experiments, in order to run their work effectively, they need to understand really in quite detail about how sites work. And then they can put the data where they need it in order to process it. And the feeling with or my view with the data lake is that we're taking services such as Rucio and FTS, and we're using that at more of an infrastructure layer. So when the experiments, whether the LHC or a different experiment comes along, they need to worry less about that. They can just interface with something like Rucio or FTS, and then the details, the specific details that, oh yeah, this site has a bit of a dodgy firewall or whatever, and so it can't transfer to this site as well. Something else is taking care of that for it. And this is especially important when we've got more heterogeneous resources, because as you know, the number of things, different types of endpoint, whether it's we get access to more HPC endpoints, or we start including many more GPUs or even FPGAs in the processing. You're going to need the ability of getting the data to the right resource to process it is going to become much more complicated and require a lot more knowledge. And so this is what's been worked on, and the aim with the data lake is to kind of use these services to intelligently move the data to the right place in a kind of just-in-time mechanism, so that when whatever work is needed to be done, it's there and can be accessed in an efficient manner. Okay, so I mentioned that. So, and now I'm going to talk about what exactly RAL is doing as part of this. So, RAL is, we very keen on being part of this for both the LHC and to try and take advantage of this for other communities that we support. And so, one of the things that we've been doing since about 2018 is we developed, and now we've deployed and we're running a multi-VO Rucio instance. So in this case, so that basically means that we're running a single instance of Rucio that can support several communities. And what this allows is that it means that if a community comes along and says, can I try out, test Rucio, you don't have to set them up a completely new instance. You basically create an account on an existing one and off they go. But it's actually kind of more useful than that, in that we can therefore share a lot of things. So not only are RAL basically running the service, which I've shown in this little diagram here, which has many different virtual machines and a database backend and monitoring and other services to to keep it highly available. So not only does the experiments not need to worry about that, but then there are certain things like the monitoring, which is then shared, because if two different experiments are using the same site to process their data, and one of them has a problem, or the site's having a problem, it'll affect both of them. So it allows users can actually then start to see, well, hang on, is it a problem with my end, or is everybody having a problem with that particular site? So it helps there as well. And so, yeah, so RAL's been developing this, and this allows basically, you know, we want to enable not just the LHC to make use of any data lake, but smaller communities as well. And as the WLCG community develops things for Rucio, we'll incorporate them. We'll keep our version upgraded to incorporate these new features, and then basically just to try and really lower the what is it, the bar in terms of actually being able to make use of these things. Because, you know, when most people come along, especially, you know, if you don't have a problem which is immediately at the exascale level, you kind of probably, you know, Rucio or many things seem very, very heavyweight. And, you know, it does take very big communities like SKA that know well in advance that they're going to need to have a very large scale project in order for them to, you know, start off, you know, trying to solve those ones immediately. Most people will say, okay, let's just start with the more contained problem. And this effectively allows us to introduce people easily. If they find it useful, they can keep using it, and if they don't, well, that's also fine. They haven't burnt many resources, you know, setting it up and actually trying it. So yeah, these are, I mean, a list of the reasons that we're kind of doing multi-VO. I mean, scalability is another one, because I mean, with Atlas, you know, we know that it scales to the exabyte level already and handles billions of files. So from our point of view, if we've got an instance that can do that, it doesn't matter if most people that will be using it are orders of magnitude, you know, a lot less, because it'll still cope. Maintenance and things, it's much easier if we've just got one instance on top of that. So that's kind of what we're working on at the moment. And I guess I couldn't think of a good conclusion slide, so I just kind of moved on to questions. But what I would say with the Multi-VO Rucio and things, that it is I mean, many people may have heard this from either ExCALIBUR or Iris or SwiftHet or Grid PP meetings, if they've ever attended them, that, or even EGI meetings, that we do have this Rucio instance. And while it may not fit your use case, it definitely works for data management at the exascale. And, you know, we're very much aiming to reduce the bar for access as low as possible. So a little bit of a plug at the end there, that if you are interested, then, you know, and we've introduced a few communities recently, we can set up a couple of hours meeting, take you through a tutorial, go by line, and then that should actually give you access to the, you know, genuine, you can start accessing the service. And you know, and then an hour later, if you decide that you absolutely hate it, well, you've just wasted an afternoon in order to do that. Anyway, that's me done. Thank you very much.
Thanks very much, Alastair. Yeah, there's three questions come in, all from Sean, as it happens. Maybe we'll take them in reverse order, because that's sort of fresh in our mind. So he asks, for the multi-VO access, you need to have a community VO to do that.
No, effectively. So there are individuals that are trying to investigate things for a, basically we've got a demo VO as well. So if there's literally, you know, one person for a community that's just like, and we've had this with quite a lot of people, you know, if you're doing a very like DRAC or LSST, when they've been saying, you know, we're going to do something three years in the future or whatever, can you just try and explain it to us? We can say, yeah, here's a demo one. We've got sites already set up, so you can literally jump in and be, oh, let me upload a file. Here's my file. Let me use the upload command, and then let me use the command to move it from wherever I am to somewhere else in the world, and see what we're doing. So yeah, we've got that. I mean, it's still kind of work in progress, but it effectively, we do have a demo instance where we can let people on, and you can just do basic, well, not basic, it's all set up for you to actually genuinely try Rucio commands.
Okay, thanks, Alastair. Maybe we covered the second one, unless I misunderstand. Is there feedback from the FTS to Rucio to tell Rucio not to send data when sites are struggling?
Yes, yeah, they are well integrated and talk to each other. So the services will back off, or try again a bit later type thing if they're struggling. And Rucio is, depending on how you said it, Rucio is intelligent enough to, if a site was to basically, if it was trying to do something to a site and then you said that site's unavailable, it would say, it can reevaluate the rules and say, right, I need to move it somewhere else because it's not at 2 sites if this site is down, if that was the rule or whatever you were making.
Okay, super. And then for the high luminosity LHC, will you be using traditional processing techniques or streaming processing?
So I'm not sure what Flink is, but so I think the thing is that I guess it's a bit of both. I mean, with the LHC, the fact that each event can be treated separately does mean that you can have a process where it's copying. It knows in advance, let me just copy this next data to in. So it is, I guess, moving to a more streaming-like setup where you only request the things that you want, but you're still the kind of, well, just here's your whole event. If it takes them 10 seconds to process an event, and an event is only a few megabytes in size, it's easy just to say, look, here's the whole one. You've got it all in memory. If you need it, then you move on to the next one. So there are certainly streaming processes that are being considered because there are certain use cases. If you are trying to just take a very small amount of data from a huge set of files, it's clearly better to use streaming for that. If you're kind of doing quite a heavy reprocessing, actually, it's kind of more just straightforward, just to be like, look, here's all your data you need. Don't worry about trying to do it efficiently, when if you need kind of 80% of the data anyway, you may as well get 100% of it. But yeah, if you're kind of requesting, if your types of analysis only need 0.1% of the data, clearly a streaming method is more suitable. And yeah, the LHC use both.
Okay. Okay. Well, maybe we'll stop there, Alastair. That was another really interesting talk.